Hi, this is Professor Dorr, and this is lecture 13 of EE310. Lecture is titled Mutual Inductance and Transformers. In this lecture, we're going to review Chapter 13, Sections 1 through 3 of Alexander and Sadiku's Electric Circuits textbook. And we're going to introduce the introductory concepts of mutually coupled circuits. And we're going to discuss the dot notation for reference polarities. And we're going to have a few good worked examples where we're really going to dig into these concepts. In this lecture and the two lectures that follow it, I'm going to connect mutual inductance and the art and science of printed circuit board design. I worked in industry for 35 years before becoming a professor, and what I noticed is that printed circuit board design is considered kind of a dark art, and there's not always a lot of science that goes into it. There are extremely talented printed circuit board designers who work from rules, and those rules are really good, and they're generally based on science. But sometimes you get a printed circuit board that just doesn't simply do what you want it to do. And I want you to be able to use the information in the next few lectures to be that engineer who can solve the most difficult PC board design problems. So we're going to do a lot of theory in the next few chapters, but I want to make that theory practical for you. I want it to be useful for you, and I want it to enable you to make more money and have more fun in your career once you go out into industry. So let's get started. What we've worked with so far are conductively coupled circuits, where we move energy around using wires. And now we're going to look at a different way of moving energy around, and we're going to do it magnetically. We're going to do it with magnetic fields, magnetic coupling. So we're going to move energy. We're going to start with in an electrical form, and then we're going to turn it into a magnetic field. Then we're going to turn it back into an electrical form. Why would we do that? Well, one is electrical isolation. You'll find, and we're actually going to do, I've augmented one of the examples to show the benefits of electrical isolation that you get from transformers. Oh, I think I said the word transformers. Good. We can also use it to step AC voltages and currents up and down very efficiently. Wouldn't be able to distribute power to all of our houses and businesses if we couldn't do that, if we didn't have transformers. And in the next few lectures, in addition to talking about transformers, I'm going to show you pictures of cool transformers and substations and things like that, so you can actually see where they live and what they look like. And another application is impedance matching for maximum power transfer. We've done a bunch of problems with maximum power transfer where we put in some reactive components and we get maximum power transfer using Thevenin circuits. What we're going to see is that transformers can be very effectively and efficiently used to get maximum power transfer. When you look inside your cell phone, you're going to see inductors in the RF front end. Inductors are heavy, they are expensive, but they are the best animal to do the job for impedance matching in your phone, in any radio receivers. And of course also, transformers are used in filters. Now, I think transformers are pretty cool. One of my favorite comments, if you look on the cover of this fine book, you're going to see a toroid on there. And it's a beautiful little toroid, and when I was looking at things I wanted on this cover, I wanted magnetically coupled circuits. Okay, so what we know, or we sort of know, is that electricity and magnetism are related by Maxwell's equations. And Maxwell's equations are pretty complicated. Everybody's seen that t-shirt that shows the Maxwell's equations, and then it says, "Let there be light" underneath the equations. Well, those are pretty complicated, and I'm not real good at visualizing all that vector calculus. But what I do is I boil it down to Faraday's law. And just one more comment about Maxwell's equations. If you make everything on 90-degree angles, then they become much easier to work with. But for our purposes, let's boil Maxwell's equations down to Faraday's law. And so what we know is that the voltage as a function of time is equal to n times d phi dt. So I've got a picture here that kind of shows it. So we've got a little toroid here, and it's actually cool. You can draw the wires around a toroid the way I did here, and even if you can't draw very well, you can show which way the wires are going and which way the flux will be going. But bottom line is I've got n turns of wire going around my coil, and okay, then you have to be social. You get up here. I'm sorry. If she's going to bug me, she's got to say hi to all of you. Say hi to everybody, Bella. And then stop bothering me. I'm trying to give a lecture. So we have our toroidal core, and this thing, it's kind of a round thing if you look at it in cross-section, and it has the wires wrapped around it the way I show here. And the equation that describes this is that the voltage that we see at these two terminals is equal to the number of turns times the rate of change of flux. So d phi dt, because flux phi is in the core here. And so that's Faraday's law. And that's really all we need for right now. The smart people that design antennas and things like that, they really got to understand Maxwell's equation, but I'll be the first to admit that I am no expert with them. So this equation is kind of written so that you can see that flux in a coil, or time varying, don't do that, time varying flux can introduce a voltage. Well, it works two ways. A voltage can introduce time-varying flux. So it works two ways here. I can shove some flux by some means through a core, and if there are some wires wrapped around it, I'm going to get a voltage. Or I can say it in the way where I introduce a voltage across these two terminals, and they're wrapped around some sort of ferromagnetic core. I'm going to introduce flux. So works two ways. Flux can induce voltage, and voltage can induce flux. So let's get ahead of ourselves a little bit. Here's a toroidal core, and again, it's a toroid, so if I were to turn it like that or cut it, it would have a circular cross-section. And I'm going to put two coils on it. And some of you might recognize this as a simple transformer. And I've got N1 turns on this side, and I've got N2 turns on this side. And so I'm not going to connect these terminals right here to anything because I don't want them to have any current for my little example right here. So what I'm going to do is I'm going to say V1 is equal to sine omega t. And that voltage is going to introduce a flux in the coil. Here's our equation. what let's do is let's say that d phi dt is equal to v over n. And so therefore my flux is going to be the integral of v over n. So this voltage introduced this flux in this core. It's kind of cool. It's an AC voltage, right? So when the voltage goes one way, all that flux is going to be shooting around that way. And then when the voltage goes through the negative part of the cycle, all that flux is going to be going this way. So that flux is going to be moving. It's going to be like when you look at a washing machine, when it's in the whatever the cycle it is, where it's whooshing everything around and trying to get lots of turbulence. So I guess all the clothes in the washing machine are going to look like our flux in this picture. Okay, so my voltage introduced the flux, and here's the flux. It's got an integral sign. But now I'm going to go to this coil, and this coil is kind of the it is the recipient of all that flux, right? Because the flux that I generated with this coil is getting linked into this coil. And of course, V equals N2 d phi dt, or V2 equals N2 d phi dt. So now the flux is going to induce a voltage over here. And I'm going to take the derivative of my integral here, and I am going to get, or in other words, the derivative of this flux is going to be just sine omega t over n1. And I put that over here, and I say V2 is equal to n2 over n1 times sine omega t. Well, that's pretty cool. We started off with sine omega t, and over here, we got n2 divided by n1 times that. So our transformer stepped up the AC voltage. And one of the things that transformers do is we step up and down voltage, and you'll see later currents. So it's really not harder than that. But in this case, this transformer is ideal. And here's why: because the core is such a happy place for a magnetic field that the magnetic field is all going to stay inside. We say the core has high permeability. So for this case, all the flux that was generated or caused by this coil stayed in the core, and every little bit of it went through here. So this is part of the definition of an ideal transformer. And we make transformers this way. If you look on the cover of this fine book, what do you see? A toroid. So here's an example of one. Now, in other cases, you might have two inductors on a PC board, and they are, as your PC designer would say, talking to each other. And now you're getting just a little bit of that flux that was produced by one inductor kind of wiggling its way over and getting in the other inductor. And that's the case we're going to talk about next. This was just to get you excited about transformers so you'll stay awake during my lecture. So we're going to introduce the ideal transformer in section 13.5, and what we're going to do now is we're going to say not all the flux is coupled by both coils. Some leaks out. And so here's kind of a picture of that. Here are two coils, and they are wrapped around some ferromagnetic cores, but the core doesn't go all the way around like it did with the toroid. What's this core? A nail. That'll work. It's not a great core, but it is ferromagnetic, and it's a pretty nice little core. It could be the little ferrite rod. If you pull a transistor radio apart and look at the antenna inside it, it's a ferrite rod. So, but the basic idea is these are separated in space. And this coil of wire is going to introduce flux in this ferrite rod. And it's all going to be in here. But some of it is going to go around and it's going to go into this core and introduce a voltage here. But not all the flux will. Some of the flux is going to kind of hang out locally, and some of the flux is going to go out to the end of the universe and come back again. But the bottom line is that the flux generated in here is not all going into here. In contrast, in this example, all the flux here went here. So as you can kind of expect, things are going to get a little more complicated than in our simple example, but not that badly. We're going to start with V of t is equal to n d phi dt. That was our Faraday's law that we pulled from Maxwell's equation. And so flux is produced by current because flux is part of a magnetic field, which comes from a current. So d phi dt is the flux change with a single turn. So what let's do is let's break d phi dt up here. So we have V equals n d phi dt. But now I'm going to say, okay, instead of having flux that just happens to be there, how do we put it in there? So we have V equals n d phi dt, but let's break d phi up into d phi di times di dt. Can I do that? Sure. My di's cancel, and I get right back to where I was. So I just split it up. And why did I do that in this derivation? Because I know that I need current in there. And also, I'm going to get something important here, which is that with V broken up like this, what do we see? We see n d phi dt times di dt. Well, doesn't this look a lot like V equals L di dt? So, yeah. So what we can see is that inductance is equal to n, the number of turns, times d phi di. So here's a nice little recipe for making an inductor. There are a lot better ones out there in Wikipedia and in the ARRL handbook, or the handbook that the ham radio operators use, because it's a wonderful guide for information. But the inductance is just n d phi di. I mean, think about it. If you want to get more d phi, you probably need, actually I won't go there. But so we have split V up into n d phi di times di dt, and then we reminded ourselves, hey, that's L di dt. Okay, so let's go down here. The flux from coil 1, the flux that was generated by these turns of wire, is really equal to, we'll call it phi1, and it's equal to phi11, which means the subscripts mean originated in 1 and just went back to 1, and phi12, which is the flux that originated in 1 and went to 2. And we'll find that that's the same as phi21. So the flux from coil 1 is equal to phi11 plus phi12. So V1 is equal to L1 di1 dt1. And L1 is the self-inductance of this coil. It's the self-inductance. Forget about coil 2. V equals L di dt. Duh, right? So now let's look at V2. Or in other words, we're squirting a current in here. We have no current over here for this derivation. We squirt a current in here, and we're going to get phi1. But the flux that goes over here is phi12. So the voltage across coil 2 is going to be N2, the number of turns here, times d phi dt in that coil. But it's d phi 21 dt, because remember, we squirted a current here, it blasted out this magnetic field, part of the magnetic field got in here, and it induced a voltage, V2. So let's look at that. V2 equals N2, number of turns, times d phi12 dt. Yeah, that sounds good. Equal, and now we're going to break that up into the d phi1 dt to d phi12 di times di1 dt. And we have something that looks again like an inductance. See that? N2 d phi12 times di1 is the mutual inductance. So what I can do is I can say that as far as V2 and I1 are related by the mutual inductance between them. So let's just work with that for a second. If they're real close together, then I'm going to get a lot more of phi11. I'm sorry, I'm going to get a lot more phi12 if they're closer together, right? And if I do that, then of course V2 is going to be greater, isn't it? Now let's move this way far away so we get like no phi12, or in other words, very little of that flux gets into that coil. Now I'm going to get a very small voltage in V2. So you can kind of see that this all kind of makes sense. But what we've described is the mutual inductance between these coils. And we can say V2 equals mutual inductance times di1 dt. So it's the same formula for inductance we use, except now we're looking at a voltage in a different place than where the current was that caused it to happen. So we had the current source over here and we generated our equations. Now what let's do is let's put the current source on the right side. And of course your intuition says, yeah, okay, it's going to be the same thing. It's going to do the same thing. And you're going to be absolutely right. So now I'm going to get V2 equals L2 di2 dt. Or in other words, L2 is what was the term we used? It's the self-inductance of coil 2. That's L2. So V2 equals L2 di2 dt. Yeah, duh. But now let's see what this current does to the voltage over here. And we see that V1 is equal to M12 times di2 dt. So di2 dt is going on here, and M21, which is going to be the same as M12, is going to dictate how much voltage we get on V1. So current here is generating a voltage over here. Current here is generating a voltage over here. we said that we couldn't have a load on the other side because things would get too complicated. So we need some housekeeping. We need some nice, concise equations to describe all this hand waving that we just went through. Let's get them. These are my favorite equations for these. V1 equals L1 di1 dt plus M21 di2 dt. V2 is equal to L2 di2 dt plus M12 di1 dt. These equations sum up all the hand waving that I just went through. So now let's define mutual inductance. And like in so many other cases, our book has these, Alexander and Sadiku, their electric circuits book, has just these beautiful definitions of things. And this one is right on the nose. Mutual inductance is the ability of one inductor to induce a voltage across a neighboring inductor, and it is measured in henries. So very nice description of what mutual inductance is. Very concise way of describing what happens in a mutually coupled circuits. Now what let's do is let's look at dots on transformers. And what dots do are they're used to connect the physical part of the coil with the equations that we use. And if you're seeing this concept for the first time, it looks just like another concept that we're blasting at you in EE310. But the dots often cause a lot of confusion for students, and students really sometimes need to come back and look at them again. And sometimes when students are doing problems, they'll come up with some other way of describing the dots because it'll work for one problem or two problems, and then it gets them in trouble. So what I want you to do is use this definition of dots, of course, well articulated from our textbook. Use this definition and only this definition. So here we go. If a current enters the dotted terminal of one coil, kind of like this current is entering the dotted terminal of this coil, the reference polarity of the mutual voltage in the second coil is going to be positive at the dotted terminal of the second coil. So the way I like to interpret that is if a current enters the dot, it makes the dot more positive on the other side. That's exactly what this says. If the current enters the dot, it makes the dot more positive on the other side. Now, why do we care about dots other than to get through EE310 problems? It's because when you buy a transformer, you'll get a data sheet, and there will be, pin 1, pin 2, pin 3, pin 4, and I gotta know how to connect pin 3 and 4, because if I connect them one way, I'm going to get one polarity, and if I connect them the other way, I'm going to get another polarity. If it's in a data communication system, that polarity change may change all the ones to zeros and all the zeros to ones. If I'm connecting up speakers in an auditorium, then the speakers are going to be out of phase, and it's going to do bad things to the acoustics. So whenever you look at a data sheet for a transformer, you're always going to see those dots on there. All right, so again, if the current enters the dot, the voltage at the dotted terminal will be positive. If the current enters the non-dot, then the voltage at the non-dot will be positive. Let's look at a few examples. So in this case, I've got a current going into the left side here. It's entering the dot, so it's going to make the dot more positive. And the way I have defined V2 here, I can say that V2 equals the mutual inductance, this is how we show it, times di1 dt, because current enters the dot, makes the dot more positive. Now, let's connect the transformer this way, and you can see that I've defined V2 as plus minus here, just like I did in this problem. But the dot is on the other side. So current goes into dot, it makes the dot more positive. But the dot side here, we defined it as the negative side. So now I'm going to say V2 as specified by my convention or my definition here, V2 is equal to minus m di1 dt. So in the next example, I'm going to squirt current into this side. You'll see we'll be calling this the secondary side of the transformer and this the primary side as we move on, but we're not ready to do that yet. So now I can say that the current is going into the non-dotted side, so it is going to make the non-dotted side here have a positive voltage with respect to here. But look how I've defined my voltage. I've defined it plus to minus. So V1 is equal to minus m di2 dt. Now let's go over here. Here I put the dots over on the bottom side of both. So I2 enters the non-dot, and so it makes the non-dot more positive. So doesn't that also mean that if I put I2 in here, it would make this end more positive? So what I can say on this one is that V1 equals m di2 dt. Okay? Because I2 made the non-dot more positive on this side, but the non-dot is defined as the plus terminal. So one thing you can see is you can say this equation would not change if both dots were down here. So in this case, two wrongs make a right. All right, let's look one more time at our definition, and this is the only definition you should use. If you think you've found something and you say, hey, this looks like it always works, make sure that it's saying this, because this is the only thing that'll always work. If the current enters the dotted terminal, it induces a positive voltage at the dot of the other terminal. Okay, let's do a cool little problem of coupled coils in series. Now, we know that if these coils were not coupled, if there was no magnetic field coming out of one and going into the other, then the series inductance of the combination would be equal to just L1 plus L2, because we have an impedance here, we have an impedance here, series impedances add, right? The way in industry you make this condition happen is you separate your coils physically, or you put shields around them so the magnetic field is so happy being close to the coil that it never strays away. So if they weren't coupled, you'd have the series inductance as just L1 plus L2. But in this case, they're coupled. As your PC board designer says, those coils are talking to each other. So let's use KVL. So V out, which I've defined as plus to minus, is going to be equal to L1 di dt, because here's I, and check it out, it's the same I going all the way through the coils. So let's just add up the voltages. I have L1 di dt. Now I'm going to get an induced voltage in this coil from this coil. So what happens? The current enters the dot of this coil, so it's going to induce a voltage that makes this voltage across this coil greater, and here it is. It is actually, no, let's not look at it that way. Let's say that this current in this coil induces a voltage over here. Sorry, what I said before was correct. It's just not the way I set the problem up. So we have a current going through this coil, and it generates a voltage across this coil, but it also generates a voltage across this coil, and since this current entered this dot, it's going to make this dot more positive, so the value of that induced voltage in coil 2 is going to be M di dt. Now the current goes into this coil, and of course it generates a voltage L2 di dt, but then it induces a voltage in this coil, and we notice the current went in the dot, so it's going to make the dot of this one more positive when it induces the voltage, and here it is. The voltage caused by current going through L2 induces in coil 1 M di dt. All these add together. All these voltages have the same polarity. And so we say V out is equal to, here, let's factor L1 and L2, or I'm sorry, let's factor di dt out. Sorry about that. And we end up with L1 plus L2 plus 2M. Let's see, V out equals L di dt. So the inductance of the series combination is going to be L1 plus L2 plus twice the mutual inductance. And this is really pretty cool, because if these coils were not coupled, the inductance would just be L1 plus L2. But because they are coupled, it's L1 plus L2 plus 2M. So now what I want to do is let's take this circuit, and we're going to disconnect this wire right here, and we're going to turn L2 180 degrees so its dot is on the other side, and then we're going to connect them back up right here. So now my circuit looks like this. And V out is again going to be from plus to minus going this way. Let's look at what the inductance of this connection is. We call this connection series aiding and this one series opposing because the dots are on different sides. So V out is going to be L1 di dt from plus to minus. That's just the self-inductance of L1. But this current through L1 is going to induce a voltage over here, and the current is entering the dot, so it's going to make the dot of this coil more positive. And therefore, I'm going to have a little plus to minus source here. Well, plus to minus gave us a positive voltage, but minus to plus gives us a negative voltage. And so the voltage induced into L2 by L1 is going to be negative M di dt. Let's keep going. Now we get to L2, and I'm going to get a voltage of L2 di dt. Same polarity as the self-inductance of this coil caused, of course. But now the current into L2 is going into the non-dotted terminal. So it's going to make the non-dotted terminal here more positive. So I'm going to have a minus to plus. And again, I'm going to have a negative sign. So if I factor di dt out, I get L1 plus L2 minus 2m di dt. And we can see that in the series opposing configuration, the inductance is actually less than what we would get if we just combine the uncoupled inductors in series. Now you can do all kinds of cool things with this idea, and I'm not going to go into them in this class, but we get into things like common mode chokes, and we get the way of making an inductor with 4 terminals that you can get different values of inductance. There's all kinds of cool stuff you can do with that. But though everything we did up here was right, boy, we did a lot of hand waving in terms of, well, we're going to have a negative to positive, which is going to offset our positive to negative. And this kind of looks like the current here induces a voltage here. And boy, there was a lot of hand waving. So what we need is some housekeeping. So let's do some housekeeping. So what I'm going to do is I'm going to move over to the phasor domain, meaning that we're going to be working with sine waves, and that's not going to limit us. So V1 equals L di1 dt plus M di2 dt, and we have a similar equation for V2. These were my favorite equations up a couple of pages ago. Let's put them into phasor form. L1, that works, and di dt is just going to be j omega I1. So when I go to the phasor, my di1 dt is just going to be j omega big I1 multiplied by L1. My next term, di2 dt, that's going to be j omega I2. Then, of course, here's my m. And the same thing holds down here. So now I have phasor equations. And let's take a look at these. J omega L1 times I1 kind of looks like just an inductor with inductance I1. Now let's look at this term. J omega M I2 kind of looks like a dependent source to me. It's a voltage source that's dependent on I2. So why can't, in a circuit, I write this just as an inductor L1 and write this as a dependent source? So I'm going to do that down here, but I want to clear something up first, which is in this case, the currents would be defined so I1 goes this way, but I2 goes in this way. And that's why I have all these nice plus signs. But now I'm going to do my I1 and I2 the way I would if I was doing mesh analysis. And let's see what we've got. So here is our equation drawn out as an actual circuit. So I1 is going to come through here, and you can see its reference polarity. It's going to be going in, and it's going to generate a voltage, j omega L1 times I1. And it's also going to induce a voltage over here. And I1 is entering the dotted terminal of this coil. I1 is entering the dotted terminal, so it is going to make the dot of this dependent source positive. So I1 enters the dot, it makes the dot over here more positive. Similarly, I have I2 going through this inductor, and I2 enters the non-dot, so it's going to make the non-dotted terminal of L1 more positive. And so that's why at the dot here, I see my negative sign. Okay, so let's revisit the series coil problem using phasors. So we want to find the inductance of this series combination. And here are our coupled coils. You can see they're in the series aiding configuration. And we're going to define VO going this way. Now, I do this as a series of steps. The first thing I do is I always draw the source between the coil and its dot. So here, I've got a coil and a dot. I kind of move that dot out a little bit, and I put the source right here. Same thing with this coil. I know it's going to need a source, so I'm just going to put it in. I'm going to move that dot over, and I'm going to draw the source between the coil and its dot. The second thing I'm going to do is say, I know the value of the induced voltage. I just don't know its polarity yet. So I'm going to write the value down. And I know that the value of this induced voltage is going to be J omega M times I2. And the voltage of this dependent source is going to be J omega M I1. Of course, I1 and I2 are the same here. So step one, put the little diamondy symbol in there between the dot and the coil. Step two, put in the magnitude of the voltage. Step three, deal with the polarity of this source. So here, the current is entering the dot of L2. So it's going to make the dot of L1 more positive. So I got a plus here and a minus here, just like I showed. Again, current enters the dot of L2. And therefore, it makes the dot of L1 more positive voltage-wise. So I have a plus to minus right there. Now let's go here. The current enters the dot of L1, so it makes the dot of L2 more positive. So now I've got a plus to minus going this way. So that's my third step, is do the polarity. So first of all, draw the diamonds between the dot and the coil. Second of all, write the magnitude of the induced voltage. Third of all, get the polarity right. Fourth of all, forget the dots. You're done with them. So here's my circuit with dependent sources. Let's add the voltages starting at the negative end. So I'm going to start here and just go up toward the positive end. V out is going to be J omega L to I. Okay, that's from plus to minus, right? Because I is going this way, so I'm at 0 here. J omega L to I. Oh, I'm going to go up again. J omega M times I. Now I'm going to go up again. J omega L1 times I. And then I'm going to go up again, J omega Mi. Let's factor out J omega I. And I have L1 plus L2 plus 2M. So a lot of housekeeping here made this problem a lot more simple than it was when I was doing all the hand waving. Now let's reverse the dot on one of the coils and recompute the inductance. So I'm going to take this coil and just turn it around so the dot is on the other side. So here we go again. Let's do our steps. First step is put the little dependent source symbol, just the diamond, no polarity, between each inductor and its dot. So I'm going to need a little diamondy thing there, and I'm going to need a little diamondy thing here. That's step one. Step 2, I know the value of these currents is going to be, in this case, j omega m I2, and here it's going to be j omega m I1. The i's are the same. So that's my second step. The third step is to assign the polarities. So let's assign the polarity for this one. It comes from L2. The current is entering the non-dotted terminal of L2, right? Because the dot is over here. Current is entering the non-dotted terminal. So what that means is the non-dotted terminal is going to be positive. So here we go. The non-dot got the positive sign. So now let's look at the current going, and here we go. Current enters the non-dot of L2. So now, for this dependent source, we see that the current enters the dot of L1, so it's going to make the dot of this coil, L2, more positive. So therefore, you notice my positive is right on my dot. And so step 4 is punt the dots. We don't need them anymore. I just have a nice circuit, and I know how to deal with circuits. Let's start at the negative end. Here's our negative end of VO. It's going to be go down j omega mi, right? Because we started here, and we're going to go down. So minus j omega mi plus j omega L2i, because that's a voltage going plus to minus, plus j omega L1i. And then here, oh, we're going down again. So minus j omega mi. So we'll factor out j omega I, and we're going to get our equivalent inductance, which is L2 plus L1 minus 2m. So what we've done here is we came up with this housekeeping method. We came up with it right from our phasors. And we said that an inductor really looks like a regular old inductor plus a dependent source. And we came up with our 4-step program for putting the dependent sources in circuits. And then we went back to our series aiding and series opposing problem and found that it made it a lot easier. Okay, let's do a problem. So in this problem, I have 2 mutually coupled coils. And in this problem, you can see that you don't need the frequency because I gave you the impedance, the self-impedance of L1 here. I gave you the self-impedance of J2. I'm sorry, of L2. And then I gave you the mutual impedance between the two. And then you can see that I've got the dots here. They're shown. So that'll help me with my polarities. But we see something weird here, which is, look at this. There's a 15,000 volt DC source on this part of the circuit. And the reason I put this here is that in the sales pitch for inductors, I told you that they were very good for isolation. And I'm going to define that here. So if I have a 15,000 volt DC source here, what's my DC voltage at this point? Think about that. What's my DC voltage at this point with respect to ground? What's my DC voltage at this point with respect to ground? Here? Well, I don't see any return path to ground. So there's no way that any current is going to flow in here due to the 15,000 volts. So therefore, I am going to, if I measured with a voltmeter from any point in this part of the circuit to ground, I'm going to get 15,000 volts. Now, let's go to this part of the circuit and let's measure with our DC voltmeter to ground. Well, the energy transfer for mutual coupling is all based on di dt's or d phi dt. But for DC, that derivative is 0. dv dt is 0. So for this DC value is not going to magnetically couple over here. So if I take my multimeter and I measure the DC from here to ground and from here to ground and here to ground, the DC value is going to be 0. But I am going to take part of this AC voltage and couple it over. So I'll see a remnant of this AC voltage, but I won't see any of the DC voltage. So we say that the transformer has given us DC isolation. People use that, engineers use that to make devices safer because the transformer will give them isolation from DC. So it was one of the sales pitches for transformers, and now you can see it. If you don't like the idea of there being 15,000 volts DC anywhere in here, go back and look at it more. There's no return path. There's no return path to DC. That DC voltage is not going to make currents go around this way. Convince yourself of that. All right, so our strategy on this problem, we want to find V out right here. So first we'll deal with the 15,000 volt source. And what we just decided is that as far as getting V out, we can just blow it off. We don't even need it because it's not going to affect V out. In other words, this transformer gave us DC isolation. I can put my hand on this part of the circuit. Well, 200 volts, maybe not, but you know what I mean. I'm not going to get zapped by 15,000 volts. Okay, so we got rid of the DC source. Next thing we're going to do is we're going to redraw this with dependent sources. Remember, that's step 1. Step 2, we are going to use the dots to, redrawing with dependent sources. And then we are, step 2 is right in the middle here. We are going to write in the value of the dependent sources. Then we're going to go step 3, and we're going to use the dots to establish the polarity of the dependent sources. Then we're going to forget about the dots, and then we're going to solve for I1 and I2. And I2 is going to be right here. And V out is going to be I2 times 10 ohms. So good strategy. Let's do it. Okay, so here is our circuit. And I've drawn in my I1 and I2, my mesh currents. And so our first step is I want to just draw the dependent source, just the diamonds first. And I'm going to draw them between the inductor and its dot. So I've done that in both cases here. Now, step 2, I'm going to draw in the value of each of those dependent sources. I know that the value of this dependent source is equal to Zm, the mutual impedance, times I1, because this voltage is induced by I1, and this voltage here is going to be Zm times I2. That's its magnitude. I'm not going to worry about the polarities yet. Now I'll worry about the polarities. So when I1 goes into the dot of L1, I1 goes into the dot of L1, it makes the dot of L2 more positive. So that means I'm going to put a plus right here and a minus right here, because I'm going to make the dot more positive. Now, when I2 goes into the dot of L2, it's going to make the dot of L1 more positive. So that means that I2 goes into the dot. I need a plus to minus right here. So now I've got my polarities. So now I'm going to blow off the dots because I don't need them anymore. And I'm left, excuse me, I'm left with just a circuit analysis problem with a couple of dependent sources. And here it is. So now let's write a couple of mesh equations. For this one, I have minus Vs. Vs is 200 and an angle of 45, plus 4I1 plus ZMI2 plus ZL1 I1. Now, does I2 go through here? Nope, not the way it works. This is a magnetically coupled circuit. I2's effect was taken into account in the dependent source here. So I start off with my basic equation. I gather my I1 and my I2 and my constants because I'm going to solve that matrix in a bit. Now let's write our second matrix, or our second equation. It is going to be Z sub m I1 plus ZL2 times I2 plus 10 times I2 equals 0. Here's the equation. And now I'm going to put that in with my terms gathered up, and I'm going to throw it in a matrix, and I'm going to get I1 and I2, and I2 is equal to, or I'm sorry, V out is equal to just I2 times 10 ohms. I2 times 10 ohms gives me the output voltage. And we have our answer. Let's do another problem. So in this problem, we want to find the mesh currents. And we've got the usual stuff. We have a power supply, an AC supply here, and we are given the impedances, so we don't care about the frequencies. We don't have to go J omega L because we're given what J omega L is, of course. I've got these two inductors, and they have a mutual impedance of J3 between them. Is this a practical problem? It's worth stopping and asking whether it is or not. Let's give this problem some practical significance. Let's say that the engineer designed this circuit with these two coils and did not expect them to couple, because engineers tend to not expect inductors to couple. Well, if they do couple, this problem and this analysis is going to tell us what the effect is. So that gives this problem some practical application. So if we know the mutual coupling or the mutual impedance, then we know what's going to happen in this circuit. Now I want you to keep that in the back of your head because that's not entirely practical yet. It's going to get practical in an example we're going to do later down the line, where we are going to figure out what the mutual coupling is based on the circuit behavior. And that is absolutely practical. Because suppose an engineer designs a circuit and says, I expected to get this over here. Then, but they don't. what we can do is look at the geometry and say, let's hypothesize mutual coupling and wiggle the value of mutual coupling around or mutual inductance around until we get the result that the engineer sees. Now we know how much mutual coupling there is. So I just turn it around a little bit, but you're going to see that in a problem down the line, and it's a very, very practical problem. So here we want to find the mesh currents. Our strategy, we're going to redraw with dependent sources. First of all, just the diamonds between the dot and the inductor. And then we're going to put in the value of each dependent source. Then we're going to put in the polarity of the dependent sources, and then we're going to forget about the dots. We're going to solve our circuit problem and get the currents. So here we go. First thing I'm going to do is draw that voltage source between the inductor and its dot. Now there's no real good reason I do that. I do it because that way I can do it the same every time, but I'm going to give you a little better reason for that several examples down the road. So I draw my voltage source between the inductor and its dot, and all I do is draw the diamond. Here I need another diamond. Here's the inductor. I squish the dot out a little bit and I put the diamond in there. Next thing I'm going to do is I'm going to put in the value of the source. And in this case, for this inductor here, the value is going to be the mutual inductance J3 times I2 minus I1. Or in other words, J3 times the actual current in this inductor, because the current's going to be I2 minus I1. And you can say, well, why didn't you do I1 minus I2? I can totally do that. All we're doing is getting the value. We haven't put the sign in yet. It can be I2 minus I1, or it can be I1 minus I2. Now, what I like to do, given that choice of I1 minus I2 or I2 minus I1, is I pick the one that goes into the dot first. So I picked I2 first because it goes in to the dot of this coil. And therefore, I know that if I have I2 minus I1 here, I2 enters the dot, so it's going to make this dot more positive, and I'm going to be plus to minus. And the I1 is going to follow along like a little dog in this equation. So again, I could have made my value I2 minus I1 or I1 minus I2. The magnitude of those is exactly the same. The polarity would just be different. But what I did is I put I2 first because I2 entered the dot. And since when I look at this expression, I see J3 I2, then I know that I2 is going to give me a positive here. And I ended up with a positive on my dot. So here it is, plus to minus. Now let's do this one. So the value of this induced voltage is going to be equal to just J3 times I1. If I wanted, I could have made this negative J3 I1. It would just mean I'd have different polarities. But I1 enters the dot, so it allows me to make the dot here more positive. And here it is, plus to minus. So I've put in my dependent sources now. The next step is to forget about the dots. I got a circuit design problem. No more dots. So here we go. Negative Vs plus I1 ZR plus Zm, which is J3, times I2 minus I1 plus I1 ZL1 plus I1 minus I2 ZL2 minus, because look, I'm going minus to plus as I'm going around here, I1 ZM equals 0. Gather up all your like terms and move on to the next one. Now we have ZM times I1, which is a plus to minus, so it's positive. And ZM was J3, so ZM times I1 plus I2 minus I1 times ZL2 plus I2 ZC equals 0. And so I gather up my like terms, and I have another equation I can throw into my matrix. I throw it into the matrix, and here are my currents, I1 and I2. Now, before we move on, I kind of want to point out something that's really a little bit silly, but sometimes people get messed up on it, is when we were on this problem up here, I said, do we have an I1 minus I2? No, because I had a purely magnetically coupled circuit. Purely magnetically coupled. And so I accounted for I2 over here. I accounted for I2 in this loop with the voltage that it induced. And the same with I1 over here. But in this problem, I have both magnetic coupling and I have conductive coupling. So here, yeah, it's I1 minus I2 times this J6, and you see that right here, or right here. So it's a pretty methodical process, and I really like breaking it up with my draw the diamond, draw the value, set the polarity, forget the dots. That really helps me, helped a lot of students, so hopefully it helps you too. Let's move on. Section 13.3, energy in a coupled circuit. So why do we care about this? We are going to, actually, before we talk about how we care about it, let's derive it. So we have this mutual inductance, M12 equals M2 equals M. But let's go up here, and I have J2 ohms, J6 ohms, and then I have J3. So if I'm sitting in a meeting with a bunch of my peers, I look at those numbers and I say, how much are they coupling? Well, J3 worth. Yeah, but you know, I'm the boss. I want to know a lots or a little. So is J3 a lot or a little? So what the smart people have done, the little toadstool, which is one of these things we land on as we do engineering problems with complicated things, but making them simple by jumping from toadstool to toadstool, is we say, let's define what we call a coefficient of coupling, a how much kind of measure. If they're not coupling at all, coefficient of coupling is 0. If they are 100% coupled, like that toroid problem we started off with, we're going to call them 100% coupled. So we're going to define this coefficient of coupling that goes from 0 to 1. Because now we can tell the boss, yeah, they're 50% coupled, they're 80% coupled, they're 2% coupled. And the boss is a lot smarter and has a lot more experience than we do, and the boss knows that if they're 5% coupled, he or she is going to have to spend a lot of money to fix that PC board, because that last 5% is really expensive to get out of there. But if they're 60% coupled, it's a ooh, Just lay out the PC board in a reasonable manner and you'll probably fix it. So that's the motivation for this. So we have our M12 and our M21, which are equal. And we know, and this is derived in the book, it's a beautiful derivation, I'm just not covering it in the lecture, that the mutual impedance, or the mutual inductance, sorry, is going to be less than or equal to root L1, L2. Beautiful. That's the thing we're looking for. It's less than or equal to root L1, L2. So less than or equal, let's say that M is actually equal to K times root L1 or L2, L1, L2, where K is going to be our coefficient of coupling, and it goes from 0 to 1. So now we have M equals K times root L1, L2. K is equal to 1, 100% coupling. They got a big permeable toroid. M equals 0. The inductors are shielded and they're miles apart from each other. So we can define the coefficient of coupling as K equals M over root L1, L2. How coupled are they? And K is between 0 and 1. So let's take a look. Here is a big old iron core, kind of like you'd see in a transformer. And the coefficient of coupling is approximately 1. If it's a transformer that you paid money for, we want that coefficient of coupling as high as possible because it makes our transformer more efficient. So in this case, M is equal to root L1, L2 because K is equal to 1. K is 1, so M has to be equal to L1, root L1, L2. Now let's take a couple of nails and we're going to put them near each other. So the K here, let's say it's a half. Coefficient of coupling is a half. Now I'm going to take this nail and I'm going to move it all the way over here. What happened to the coefficient of coupling? Well, the two inductances stayed the same. The mutual inductance is going to decrease because I'm not going to get nearly as much flux from here going into here if I move this one way far away. So I'm going to say the coefficient of coupling is going to go way, way down. Now what I'm going to do is let's play with geometry. Let's take nail number 2 here and rotate it 90 degrees. Well, now, instead of the field coming out of this one and going right down happily into that one, now it's going to go orthogonally through this coil. And I'm going to get maybe not no coupling, but darn near no coupling. So K goes from a half to 0. Is this practical? You bet it's practical. Say we have 2 inductors on a PC board and we don't want them to couple, but we need them in our filter. So we need these discrete inductors, but we don't want them talking to each other with their magnetic fields. But we got to put them close together because we're making a small gizmo like a cell phone. So what the PC board designer at your company knows is if you got to put inductors close to each other, put them at 90 degrees. So take a look at an RF circuit board and what you'll see is many of the coils, the coils that are close to each other, excuse me, will be at 90 degree angles because that limits, it reduces the mutual coupling. Okay, so in our next lecture, we're going to take these concepts and we're going to talk about ideal transformers, which are transformers where the coefficient of coupling is assumed to be 1. And with a good transformer, it's very close. And we're going to do cool things like impedance matching with them. So as always, I look forward to seeing you in office hour, and I will see you in our next lecture.